Welcome to the NPTEL online course on fractals and multifractals. In the last class, we have defined the hyperspace of the complete metric space and defined the Hausdorff distance on the space. Then we established that with respect to the Hausdorff distance, the hyperspace forms the metric space. That space we are calling as the Hausdorff metric space. So, in this lecture we are going to discuss some properties related with the Hausdorff metric space, which help us to construct the fractal in the hyperspace with the help of Banach fixed point theorems. So, let us define what is the dilation of the set A in the hyperspace of H of x. You can take an set A in the hyperspace of H of x, and for any positive real number, then A plus epsilon is defined as, for any x belongs to x, the distance between x and A must be less than or equal to epsilon, is called the dilation of A. First, we need to prove that for all A belongs to H of x, that means if you are taking any element in the hyperspace of x and for any epsilon greater than 0, the set A plus epsilon is closed. This we are going to prove now. Now, we already know that H of x is a metric space. Now, let A belongs to H of x, we can take any element in H of x. Suppose epsilon is 0, epsilon is 0, that means the distance between x and A is 0, then it is clear that A plus epsilon is nothing but A plus epsilon is nothing but A. So, A plus epsilon is closed. Since A is taken from H of x, if you are taking any A in the H of x, it is a non-empty compact set. So, A is a compact set, it follow from that A is compact, A is a closed and bounded, therefore, it is A plus epsilon is closed. If you are taking epsilon as the positive number, and let x be the limit point of A plus epsilon, that means the dilation of A. Then we need to prove that if x, this limit point, is a member of this A plus epsilon, then we can say that this is the closed set as per the definition of the closed set. Now, it is enough to show that x belongs to A plus epsilon, that is, distance between x and A must be less than epsilon. Okay. As x is the limit point of A plus epsilon, we are assuming that x is a limit point of epsilon. Therefore, there exists sequence xn in A plus epsilon such that this sequence must converge to the point x. Since xn belongs to A plus epsilon for all n, we have distance between xn and A is less than or equal to epsilon for all n, because the sequence is taken from the dilation of A. Therefore, the distance between xn and A is less than or equal to epsilon. Now, for each n, there exists a n belongs to A such that distance between xn and A, which is equal to distance between xn and an, since that xn is taken from n. So, each n there should be a one member in A such that their distance are equal. Thus, distance between xn and an is less than or equal to epsilon for all n. Then, since the set A is a member of H of x, so A is a compact set. So, by the definition of the compactness, if you are taking every sequence of an in A as a convergent subsequence, the compact means every open cover has a finite subcover, or alternatively we can define compactness as, if we are taking the sequence, that sequence has a convergent subsequence, we can say the set is a compact. Here we are taking an in A, therefore this an has a convergent subsequence. So the sequence an has a subsequence ank which is converged to the point in A. Assume that this sequence ank is convergent to A. This sequence is convergent to A. Since xn is convergent to x, the subsequence xnk of xn also convergence to x. Hence, if a sequence xn convergent to x, if you are taking any subsequence of a sequence, it is also convergent to the same sequence. Hence, distance between this subsequence of xn and this subsequence of an, which is implies distance between x and a. Then the distance between xn and an is epsilon, that we already written here. The distance between xn and an is less than or equal to epsilon, which implies that distance between this subsequent ank, xnk and ank both are less than or equal to epsilon for all k. Taking the limit, we can get distance between x comma a is less than or equal to epsilon. Hence, one can arrive distance between x comma a less than or equal to epsilon. Thus, x belongs to a. So, if that means the distance between x and a is less than epsilon, then x belongs to a. So, we have take x is a limit of the sequence. That limit is also belongs to a, then this becomes that a is a closed. That means a plus epsilon is a closed set. For example, if you are taking a as 0, 1, then the dilation of a with epsilon equal to 0.5 is estimated by a plus 0.5 is, you have to take all the point, the distance between x and a must be less than or equal to 0.5. Now, we are taking a as 0, 1 and we are fixing epsilon as 0.5. If you are finding this neighborhood, one can get closed interval minus 0.5 comma, this is not a full stop, comma 1.5. That means, it is taking the dilation of 0, 1 and it increased to left, right side is 1.5 and the left side is 0.5. So, it will get minus 0.5. We are taking the less than or equal to, therefore, we are getting the closed interval minus 0.5 to 1.5. Next theorem, if you are taking two element in the hyperspace and for any epsilon greater than 0, the distance, Hausdorff distance between a comma b is less than or equal to epsilon if and only if a is contained in the dilation of b and b is contained in the dilation of a. We are taking two element in the Hausdorff metric space, and for arbitrary positive real number, the distance between Hausdorff distance between a and b is less than epsilon if and only if a is contained in b plus epsilon, that means the dilation of b, and b is contained in the dilation of a with respect to the same epsilon. Now, suppose we assume that this is true, then we need to prove a is contained in b plus epsilon and b is contained in a plus epsilon. Then the maximum of, as per the definition of the Hausdorff distance, the maximum of distance between a and b and the distance between b and a is less than epsilon. Thus, if maximum is less than epsilon, then both the quantity individually less than or equal to epsilon. Then it is enough to show that d of a comma b is less than epsilon, which implies that a is contained in b plus epsilon. If you prove that d of a comma b is less than or equal to epsilon, if and only if a is contained in b plus epsilon. So, assume that d of a comma b is less than epsilon, assuming this part, and we are proving this one, then assume this one, then we will come to this part. Assuming a comma b is less than or equal to epsilon, then for every a belongs to a, we have distance between a comma b is less than or equal to epsilon, since the d of a comma b is epsilon. Hence, for each a belongs to a and a belongs to b plus epsilon, therefore, a is contained in b plus epsilon. For each a and a belongs to b plus epsilon, therefore, a is contained in b plus epsilon from this one. Then, for the converse one, so we assumed this one and obtained this one. Now, we assume this one is true. Conversely, assume this one is true, then for every a belongs to a, we have distance of a comma b is less than epsilon. We have the similar argument, distance of a comma b less than epsilon, which implies that distance of a comma b is less than or equal to b, because a is a subset of b plus epsilon. If you are taking any element in a that has the dilation d of a comma b is less than epsilon, because any member of a is a member of the dilation of b plus epsilon. So, which implies that d of a comma b is less than or equal to epsilon, which proves that if you are taking any two element, distance between a and b in h of a less than or equal to epsilon, if and only is a is contained in b plus epsilon and b is contained in a plus epsilon. The next definition, let S be a subset of the metric space x comma d is totally bounded, if for each epsilon greater than 0, there is a finite set of points y1, y2, yn, which is a subset in S, such that whenever x belongs to S, whenever this x belongs to S, distance between x and yi is less than epsilon for some yi belongs to this finite set of points. This finite set of points is called an epsilon net. So, in the closed interval 0 comma 1 is totally bounded set. The closed interval 0 comma 1 which is a subset of R is a totally bounded. Every finite subset of R is totally bounded. If you are taking any finite set, it is a totally bounded set. The space R, the metric space R with the Euclidean matrix is not a totally bounded. R with Euclidean matrix is not a totally bounded set. Now, consider the sequence A n of totally bounded subset of X. All the A n's are subset of X as well as the totally bounded. Let A be a any subset of X, A n's are totally bounded subset of X. For each epsilon greater than 0, there exists a positive integer n such that A is this set A is subset of the dilation of A n plus epsilon. Then if this is true, then A is a totally bounded set. If A is subset of A n plus epsilon, then we can call A is a totally bounded set. For proving this one, for a given epsilon greater than 0, you can choose a positive integer n such that A is subset of the dilation of A n plus epsilon by 4. If any epsilon is 2, then we can find the suitable epsilon, then A is contained in this number. Since A n is totally bounded sets, A n is totally bounded sets, because we are taking the A n from this the sequence totally bounded sequence. There exists a finite set x n belongs to A n such where n lies between 1 to k, such that an is containing in the union of the ball of xn comma epsilon by 4 as the definition of an. Then, so without loss of generality, assume that this ball with the center xn and radius epsilon by 2 intersect A, there is a common points for all the n lies between 1 and k, and the intersection is empty for k less than or equal to n. So, for each n belongs to 1 to k, choose yn as, if you are taking n from this interval, choose yn as the ball with the bn of center and epsilon by 2 intersect A with the common point. Let A belongs to A. Let take A belongs to A. To prove A is totally bounded, it is enough to prove that A is a subset of union of n from n to 1 to k, the ball of yn comma epsilon. That is, A belongs to ball of yn comma epsilon, because let we are taking A is a random number in A. Now, we are taking, let A belongs to A, we are taking, if this is one belongs to this one, then we can say A is a totally bounded set. Now, we are taking A in the set A, small a in the set, it gives that the A belongs to A n plus epsilon by 4. So, distance between A and A n is less than or equal to epsilon by 4. By the remark which we given in the previous slide, there exists x n belongs to A n such that distance between A comma B equal to distance between A comma A n. Because A we are taking as a compact set, there exists a number in the sequence, the distance between A and x n and distance between A and x A n. Then distance between A and x n less than or equal to distance between A and x plus distance between x and x n. So, this is also epsilon by 4, this is also epsilon by 4, then one can get epsilon by 2. Hence, x belongs to x n with the radius epsilon by 2, x belongs to the center x n and epsilon by 2 radius ball for some n between 1 and k. Now, thus y n belongs to this ball intersection A such that distance between x n and y n is less than epsilon by 2. Y n also belongs to here. So, therefore, the distance between these two element is less than epsilon by 2. It follows that distance between A and y n, we can write the triangle inequality, distance between A and x n plus distance between x n and y n. This quantity is epsilon by 2 and this quantity is epsilon by 2, one can get, which is less than the epsilon. Therefore, for A belongs to A, there exists y n in 1 to k such that A belongs to ball of y n comma epsilon. Hence, A is a subset of union of n to k ball of y n comma epsilon. So, A is subset of this one, thus A is a totally bounded subset of X. A is a totally bounded subset of A. We achieve by proving A belongs to A, and we are proving that if we are taking A here for our arbitrary A in A and we arrived at this one, therefore, A is a subset of this one, then A is a totally bounded subset of K. So, we proved that the dilations and the totally boundedness of the set A, and more references one can use the Professor M.S. Barnsley reference book for the more detailed proof. So, in this lecture we have proved some properties of the Hausdorff metric space, and its how to define the dilation in the Hausdorff metric space, and proved that the dilation is the closed set, and we achieved that. How to say an element in a Hausdorff metric space is the totally bounded. Thank you.